We're here with another lecture from organic chemistry. And the course that I teach in Oklahoma State University is CHEM 3013, is Survey of Organic Chemistry. And welcome back with another lecture from organic chemistry. And here we have a molecule that we're trying to find a second resonance structure for it. Okay, but first thing that you need to do, you need to be sure that all your heteroatoms are acted. Okay, so I'm going to go after oxygen. Oxygen clearly is not acted, so this is the proof for it. 2 plus 2 is 4. Okay, what's the first 2? Here, 1, 2, and what's the second 2? We made 2 bonds. So oxygen is missing 4 electrons to be acted. Okay, I give it 2 lone pair. How about nitrogen? Nitrogen, I go 3 plus 3. We have a 3 sigma bond, or we made 3 sigma bonds. We have 3 electrons around nitrogen. So nitrogen is missing 2 electrons to be acted. And I'm gonna give it a lone pair. Okay. Now, can I move this, can I move this bond and share it with nitrogen here? No need. Okay, why? Because nitrogen is already acted, and that's not going to be a cool, resonance structure. It's going to be completely wrong because nitrogen cannot have more than 8 electrons. But how about this? Can we give these 2 electrons here, share them with carbon, and they take those 2 electrons and give them to oxygen, show it as a third lone pair? Yes, it's possible. Okay, so we're going to get this. We're going to get nitrogen. We'll use that lone pair, and it will make double bond here. And then you'll have oxygen. Oxygen will take, okay. Oxygen will take those 2 electrons, and it will show up as, they will show up as lone pair, the third lone pair, and oxygen. Now, check the formal charges. Formal charge for nitrogen. Okay, if I draw a circle around it, it will be nitrogen is a group 5. I see only 4 electrons around this, so it will be +1. How about oxygen? Oxygen is a group 6, but I see 7 electrons around it, so it's -1. Okay. Now, -1 plus 1. How about the starting point? The starting point, we had the formal charge 0, and that one also 0. Okay. What's the best Lewis structure? A or B? Okay. A or B? Which one is more stable? Clearly, A is more stable than B. Why? Because it has all atoms are acted, and also the formal charges are equal to 0. So A is the best Lewis structure. Okay. We will continue the slide. We will continue the lecture talking about resonance structures, and I already showed you a couple of examples about them. I'm not going to go again. And if you have lone pair close to a positive or negative positive charge, you can share it with the carbon or atom that has a positive charge to eliminate the positive charge, like from technically carbon, or to move it to another atom, and that's going to make the system stable. But the cost for it, oxygen, or nitrogen, it will have a positive charge. And for example, in this case, you can draw it this way. You can share one of the lone pair from oxygen with neighbor carbon, and positive charge will disappear from carbon, and it will move, and it's going to show up on oxygen. Okay, so now carbon is acted. Carbon will be happy. Oxygen is, let's see, oxygen is acted as well, but oxygen got +1 charge. Electronegativity of oxygen is higher than electronegativity of carbon. So electronegativity says oxygen should not be the one with a positive charge, but you managed to make carbon acted. Okay, so that's going to give some stabilization to the system, but under any condition, both of them, they will be unstable. They are unstable. They are unstable. It's not like forever. You can keep it as it is, but it will add some stabilization to the system. Okay, so the lifetime will go up, and you can maybe, detect such an intermediate. Okay. I already mentioned that we can have different resonance structure for benzene. So I can move the double bond here, there, and another one. I can keep changing position of the double bond and start from here, there, there. So as you see, like the double bond, it keeps moving. So for example, if I start with this one, double bond used to be there, now is here, and the third time is there. Okay. And you get a system that we call it a conjugated. What does it mean? It means that, you know, like technically you have a system that's involved in a pi bond, okay? And the pi bonds, they can move, okay? They can move here, and like they can actually form double bond with, you know, in another position, okay? And later on, we will be talking about conjugated system, okay, and what will happen if we create a positive charge on them. But for now, let's keep it as it is, that we can have 3 resonance structures for benzene, okay? And I want to talk about like whenever we draw resonance structure, how can we figure whether this is going to be the best Lewis structure or the minor one, and what do I need to follow, you know, beside the octet rules, okay? And I'm gonna practice a couple of them for you guys, okay? And we're gonna start with this one, okay? First thing is, like, we need to make all the atoms octet. And for heteroatom, like nitrogen, oxygen, fluorine, they don't show the lone pair on them. So you have to start with lone pairs. Okay, show the lone pairs on them. Okay, next. Carbon is octet, nitrogen octet, and second nitrogen octet. There is no charge here. Okay, currently there is no charge here. Let's double check. Yes, I don't see a charge. Now, can I share this lone pair, okay, yellow one, share it with carbon? And if I do it, let's see what will happen. Okay, if we do it, we get nitrogen attached to 2 hydrogen, and then we will have a double bond, okay, with carbon, and this carbon is going to have hydrogen, and that bond, it will move and it will be located on nitrogen. So nitrogen will have technically two lone pairs. Used to have one, now is gaining the second lone pair. And of course, there is hydrogen attached to it. Okay. Now, how about the formal charge? Okay, let's check. Now, this nitrogen, okay, this nitrogen, and when I say this, I'm talking about this one. And that nitrogen, okay, is a group 5. I see 6 electrons around it, so it will be okay, it will be -1. How about the first nitrogen? First nitrogen is a group 5, but I see only 4 electrons around it, so it will be +1. Okay, that means the +1 will be canceled by -1, and the system will be neutral. Okay, the starting point, we had 0 formal charge here and 0 there. Okay, until now, which one is which one is stronger, is better, like Lewis structure? The one on the left. Okay, let's call this one 1, and call that one and 2. Okay, that's one possibility. Okay, and another possibility that you can do, you can you know, like take number 2 and move. Okay, move those 2 electrons, move them to nitrogen. So if I move those 2 electrons to nitrogen, okay, nitrogen will get a lone pair, but carbon, it will not be octet. Okay, so if I do it, I get carbon attached to hydrogen. That nitrogen, it has 2 lone pairs. Okay, now this nitrogen got new lone pair, so now we have hydrogen and hydrogen. Okay, let's check. Okay, let's check them. Okay, the one on the right, nitrogen on the right, we did not change it, so this one stay as it is. The formal charge for it, it will be -1. Okay, but how about oxygen? How about carbon? Carbon, okay, it's a group 4. It's not right now. It's not active. It's group 4, but I see only 3 electrons around it. So now carbon is +1. Okay, and it's not active. How about this nitrogen? Next nitrogen. If I draw a circle around it, nitrogen is a group 5. I see 5 electrons around it, so it will be 0. Okay, now the formal charge for this nitrogen is 0. We have +1 and -1. Okay, let's call this one number 3. Okay, number 3. What's the best Lewis structure? The best Lewis structure, it will be the best one. It will be number 1. So major contribution comes from number 1. Okay, from number 1. So is the major contributor technically. And number 2 and 3 are not really good at Lewis structure. Why? Because we have a positive, negative charges there. And especially number 3 carbon is not acted, and that's going to be maybe the worst structure. Okay, so if I want to order them, I'm going to say the best structure, number 1 is the best structure. Okay, number 1, it will have the lowest energy. That means it's going to be the best structure. And then number 2, okay, number 2 has higher energy than number 1. That means it's less stable than number 1. And the worst structure, it will be number 3. Okay, this is going to be the worst. Okay, the worst structure. Okay, so number 3 is going to be the worst structure. Okay, because we got carbon not only is not acted, we got positive charge also on carbon and negative charge on nitrogen. Okay, another example, we have oxygen, a neighbor with carbon. Okay, they might give you this, and instead of putting lone pair, okay, they might do this. Okay, they show you like the structure like that. Okay, now, because you have oxygen, by default, you have to say oxygen must be active. So let's give oxygen enough electron to make it active. Okay, so here you go. I'm going to give oxygen 6 electrons and make it active. Okay, now what's the formal charge for oxygen? If I draw a circle around it, it will be 7. And 7 plus 1, it will be 8. Oxygen group 6. I see 7 electrons around it. It will be -1. So oxygen has negative charge. Okay, so this species has a negative charge. Now, can I share this lone pair with carbon and then move this double bond to carbon? Let's see. If we do that one, we get such a structure. We get CH3, and then we get carbon. Carbon will have a double bond with oxygen. Oxygen used to have 3 lone pairs. Now oxygen will have only 2 lone pairs. Now, how about carbon? How about this carbon? This carbon has 2 hydrogens. And we gave it the double bond. The double bond comes with 2 electrons. So that means it's going to have a lone pair. If you have a lone pair on carbon, that means this is going to be -1. And you can do the calculation for it. How about oxygen? If you draw a circle around oxygen, it will be 0. Okay, so I got the formal charge 0 and -1. And the previous one, we had it -1 on oxygen and 0 on carbon. Okay. Now, question. Okay. This is going to be your first question. What's the best Lewis structure? Okay. Okay. What's the best Lewis structure? A or B? Okay. I already showed you the charges for them, like 2 resonance structures that we can have. And now I'm asking you, what's the best Lewis structure? Okay. Let's finish it with this example. Okay. So here, we can take this lone pair and share it with carbon, and then the double bond is going to move there. And if that's happened, we will have oxygen with 2 lone pairs. Oxygen with 2 lone pairs, and oxygen is already attached to hydrogen. Okay, we will have a single bond with carbon, and carbon attached to nitrogen. Nitrogen attached to 2 hydrogens. Okay, what happened with the lone pair? The lone pair, we shared it here with carbon. Now, if you check the formal charges, okay, nitrogen is going to have a +1 formal charge. Okay, carbon will be 0, and this oxygen also will be 0. Okay, what was the formal charge of oxygen at the beginning? So let me make it clear here. What was formal charge of oxygen at the beginning? Okay, formal charge for oxygen. Oxygen is a group 6. So I'm going to say 6 minus how many electrons around it do I see? I see 5 of them. It will be +1. Okay, A versus B. Okay, what's the best Lewis structure? Okay, the top one, it has the positive charge on oxygen. All here, the second one, it has the positive charge on nitrogen. Okay, electronegativity of oxygen is higher than electronegativity of nitrogen. So if we are supposed to have a positive charge, it should be on nitrogen, not oxygen. So the best Lewis structure in this case is going to be, oh, forgive me, this one is nitrogen. The best Lewis structure in this case is going to be B, or the major contributor. Okay. This is going to be the major contributor. Okay. I think we practice enough about resonance structures, how to get the formal charge, how to make them acted. And last thing from this chapter that I want to mention, in this table, I want you to get used to the functional group. And if you learn this table, if you make a flashcards for yourself and learn the functional groups, it's going to be really, really helpful to understand what type of chemical reaction you're dealing with, or by just seeing the symbol, you can easily predict the chemical reaction or maybe physical or chemical properties of that compound, and also the name as well. So I highly encourage you to memorize this table, the functional groups, their name, and they also some examples. And I will see you very soon, and thank you again.